Hi, I am Shu-Heng Lin. Today I will present our work titled Fully Polar Coordinate Object Detection, a Constraint-Based Polar Bounding Box Approach for LiDAR and Scanning Radar. This work was conducted under the supervision of Professor Chieh-Chih Wang and Professor Wen-Chieh Lin. In autonomous vehicles, detection and segmentation are core components of the perception system. They allow the vehicle to understand and interact with its surroundings. Among different sensors, range sensors such as LiDAR and radar play a crucial role. Their measurements can be naturally projected onto 2D polar coordinates, defined by range and azimuth. This figure shows an example of LiDAR voxelization using a polar-based voxel grid. As we can see in the figure, polar voxel grids naturally match the density of the points. In near-field regions, where points are dense, the grid uses smaller cells to provide higher resolution. In far-field regions, where points are sparse, the grid becomes larger. This adaptive design helps preserve fine geometric details near the sensor, while reducing computation in distant regions. We can also observe that LiDAR points often form ring-shaped patterns, which align well with polar-based grids. So overall, polar coordinates naturally align with range sensor data and help handle its non-uniform sparsity and spatial distribution. In contrast, the most common approach, Cartesian voxel grids, uses a uniform partition, where all cells have the same size. This often compresses dense regions near the sensor and wastes computation on far-field regions with sparse point density. Because of these advantages, polar coordinates have been widely adopted for segmentation tasks in recent years, and studies have shown clear advantages over Cartesian-based approaches. However, when it comes to object detection, another key perception task, polar coordinates are still rarely used. This is exactly the problem our work focuses on. To understand why this happens, we look at the evaluation metric. In object detection, objects are evaluated as a whole, typically using bounding box IOU, which makes the task heavily dependent on the bounding box representation. Since most annotations are defined in Cartesian coordinates, converting them into polar coordinates can introduce distortion, giving Cartesian-based methods a natural advantage. In contrast, segmentation relies on point-wise evaluation rather than object-level structures. Based on this observation, we rethink object detection from the perspective of the evaluation metric. Our main contribution is the design of a constraint-based polar bounding box. We project conventional Cartesian bounding boxes into polar coordinates, and then apply two constraints to generate bounding boxes directly in the polar representation. With these constraints, polar bounding boxes can be automatically generated for both training and evaluation. Our experiments reveal an interesting trend across different ranges. As shown in this AP range curve, polar representation improves detection for medium and far-field objects. As we mentioned earlier, this is related to how spatial grids distribute points with distance. Cartesian uses a uniform partition, which leads to fewer points per cell at longer ranges and thus degraded performance. In contrast, polar representation alleviates this issue and improves detection at medium and far field. However, near-field objects are heavily distorted and occupy large pixel regions, making them difficult to represent accurately with a single rectangular bounding box. Based on this observation, we define our problem scope as enhancing detection beyond 11.5 meters, highlighting the advantages of a fully polar-based approach for safety-critical long-range perception and high-speed motion planning. To summarize, our contributions are as follows. First, we propose a constraint-based polar bounding box, which converts conventional Cartesian ground truth into polar bounding boxes. This enables a fully polar coordinates object detection, without relying on Cartesian-based evaluation metrics. Second, we analyze two types of constraints and three possible bounding box definitions, and identify the most effective formulation for defining. More details will be discussed in the methods section. Third, we introduce polar-specific improvements, including ring convolution, removal of Swin masking, azimuthal shift, and polar-based augmentation to better handle azimuthal continuity and geometry. Finally, in addition to experiments on LiDAR data, we also evaluate our approach on the more challenging scanning radar dataset. The results show that our method achieves superior detection performance at medium and far field, outperforming existing state-of-the-art methods. Next, we describe our method. First, a straightforward approach for defining a polar bounding box on point clouds is to use a MBR algorithm. However, bounding boxes defined this way disregard the relationship between an object's geometric features and its orientation, which limits their accuracy. To address this, we introduced two additional constraints to better capture object geometry and improve detection performance. We introduced two constraints, a box constraint and an orientation constraint. The box constraint computes the MBR by projecting each Cartesian bounding box into polar coordinates and using the resulting curvilinear shape, rather than directly from the enclosed points. The orientation constraint enforces the ground truth orientation by projecting polar coordinates, instead of relying on the orientation induced by the MBR itself. The bounding boxes under the three constraints are shown in varying shades of orange. We analyzed these three bounding box definitions across different ranges. For very close objects, the point density is high and objects occupy many pixels. This makes it difficult for any single bounding box definition to approximate their shape accurately. For near-to-midfield objects, the network tends to rely more on features at the object level to infer orientation, so applying the orientation constraint leads to more appropriate definition. For midfield objects, the distortion is minimal and the shapes are similar to Cartesian boxes. Both the box and orientation constraints work well, though partial occlusion or sparse points can still cause challenges. For far-field objects, the point density is low. Without the box constraint, deriving an MBR directly from the object points may produce an overly small bounding box, which can affect the IOU calculation during training and evaluation. Based on this analysis, we adopt two bounding box definitions for further use. For mid and far-range objects, we use both the box and orientation constraints, while for near-to-mid-range objects, we use the orientation constraint only. We build on Partner, a state-of-the-art transformer-based detector in polar coordinates. We extend it by replacing Cartesian ground truth with our constraint-based polar bounding boxes and applying a polar-specific data augmentation. We also modify convolution and attention by using ring convolution and removing unnecessary Swin transformer masking to better preserve azimuthal continuity. Finally, we apply an azimuthal shift during loss computation, NMS, and evaluation to prevent objects from splitting across azimuthal boundaries. Here we show the experimental results on LiDAR data. We use Partner as the baseline. This model takes polar input and predicts Cartesian bounding boxes. We also run a Cartesian input version, which we call Partner C. In this setup, both input and output are Cartesian coordinates, representing a conventional Cartesian-based detector. The results clearly show that our fully polar approach outperforms both the original Partner and the Cartesian-based Partner C across all metrics. A similar trend is observed on the more challenging radar data, which has longer detection ranges and sparser, noisier measurements. Our approach demonstrates greater robustness, achieving a 13.11% improvement over the baseline. The baseline Partner model fails under these conditions, likely due to its difficulty in reconstructing object features from polar representations under such degraded conditions. This concludes my presentation. Questions about our work are welcome, and please feel free to contact me. Thanks for your attention.